Okay, so good morning, everyone. You can hear me in the back okay? All right, so a couple announcements as we begin today. First of all, remember that the peer reviews of the term papers are due at 11:59 tonight. Again, keep in mind that the Blackboard system is extremely rigid on the deadline, which is to say if you have not submitted the reviews by 11:59, you will not be able to. Even if you've got the window open and you're working on the review, if 11:59:00 hits and they're not submitted, they won't be submitted. And there's nothing I can do to override that. So please, I know a lot of you have already completed them. Thank you for that. Please get those reviews in by the end of the day today. And then likewise, it should be at 11:59. It might take it a minute. It might not be until midnight. But sometime tonight, the reviews that your peers left you should be available, again, through that same assignment portal where you submitted the first draft, where you're doing the reviews. If you go to that after 11:59 tonight, you should be able to then see the reviews that were left for you. Take a look at them. Either, maybe there's some changes you want to make to your term paper in response to them. Maybe you just want to ignore them. That is entirely your prerogative. It is not necessarily uncommon for you to get one review that might be really, really good and say this is a great paper, and one review to say there's a lot of work that needs to be done, and two reviews that are sort of in the middle. If you get an inconsistent result like that, use your best judgment. That's what the reviews are for, is to help you try to identify are there places you can improve your paper. The end decision is up to you, whether you make changes or not. In the coming days, it'll probably be tomorrow or Friday, I will then post the submission portal for the final draft, which is due next Wednesday, and it'll be due by the end of the day. Okay? Any questions then as we sort of finish up this term paper project? Okay. Other announcement, remember that homework 6, we're going to finish our search engines unit today without much issue. The homework was posted Monday. It will be due Monday at the start of class. I also posted an announcement to this effect as I was preparing today's slides. Some of the slide numbers changed. If you had already downloaded the document before last night, number 5 was going to reference slide 51 in the notes. You can find the slide numbers down here in the lower right-hand corner. It's now slide 52. I fixed the document and I re-uploaded it last night, but if you had already downloaded it, either just note it's off by 1 or go download the new one. So that's there. Come to office hours if you have questions. Post them on the Blackboard discussion forum. It'll be due Monday morning, and we'll have the quiz for that unit next Wednesday at the end of class. Okay. Any sort of other questions before we dive in? Yes?
Since we're getting close to the end of the semester, is there any way that we can know our grade in the class?
So is there any way to know your grade in the class right now? Sure. You've got everything posted on Blackboard. Take the average of your homework and drop one. Take the average of your quizzes and drop one. Right now it's sort of hard to say because the term paper is such a large component that's just sort of missing right now. Certainly what we plan to do is by the end of the semester, like by the last day of classes, have everything tabulated since the final is optional and tell you sort of here's where you stand right now, and then help you to make then the informed decision whether you want to stick around to the bloody end of finals week to take this exam or not. It's not the last day of finals, it's the second to last day of finals, and it's at 8 in the morning. Cheers. But I will give you the information so that you can decide whether or not you want to stick around to the very, very end. What was that? The quiz. So the quizzes, right. So that's sort of the other thing. I posted grades for the quizzes. David's done grading them. Unfortunately, David had to unexpectedly be off campus today, and he has the quizzes. So we will return them on Monday. I apologize that they're not here, but that was just, when he has them and he's not here, I can't return them. If you know a way to solve that problem, please let me know. Okay, other questions? And I know we'll discuss one of the questions on the quiz. I think a lot of people were sort of, if you remember the quiz from last week, were curious what disjoint meant when it came to cycles. Okay, we'll talk about that next week when we've got the quizzes in front of us. Okay, or if you don't want to wait until Monday, go look at the notes. At sort of near the end of the lecture notes from the organ donation unit. Okay, so any other questions before we finish up our search engines unit? Okay, if not, then like I said, we're going to continue with the search engines today, but in a bit of a different theme. Before we move on, I just sort of want to recap what we did last time. So we've had sort of this warm-up puzzle for this unit where we've got this comparing things. You have a list of numbers, and you want to sort the list. At a minimum, how many pairs of numbers do you have to compare to do this? For the first time this semester, we've actually answered the question. Actually, it's the second time. Sorry. We've actually answered this question last time. Does anybody remember what is that minimum number of comparisons you have to use to actually sort the list? 0. We saw this radix sort idea last time, where we could sort this list without ever actually comparing any two numbers. Which, to me, I just thought that was a really cool thing when I saw it the first time and was rather counterintuitive. So what we've been doing so far in the search engine unit was thinking about how do the search engines sort all of these web pages. So again, the general idea, search engines come in and they've got these spiders that go out and they have to build this catalog with all of this information, what's available online. Okay? Once they've done that, you as the user then come in and say, I want to find cat videos. And so Google then goes and looks through this big database over all of the resources that it has in that database to try to figure out what things are going to have information or content related to cat videos. And it's going to assign some sort of relevance score to say, well, maybe if the relevance score is 100, this is really relevant, and if it's 0, it's not relevant at all. Most things are going to probably be somewhere in between. And after it's done that, it's going to then try to sort all of those to show you the most relevant pages first when it returns those search hits. Okay? And so what we were looking at was how do we actually go about doing the sorting, but more than that, with Google or Yahoo or Bing working with millions, if not billions of web pages, we need efficient ways to sort to make this happen basically in a reasonable amount of time. We're not willing to wait 30 minutes for Google or Bing or Yahoo to provide these results to us. And that's what we've largely been focusing on through this asymptotic analysis, and then we had some of those other examples on how to do sorting last time. What I want to do today, as we finish up this unit, is try to think about in some way, how does the website actually determine that relevance score? Now again, everything we're going to talk about today is about 20 years old. The actual algorithms that Google or Yahoo or Bing use to do this are proprietary. This is what makes them their money. If they were to publish these algorithms or make them public knowledge, then in principle you could go out and you could just make your own version of Yahoo or Bing or Google or whichever one, and suddenly you're competing with them for all of that ad revenue and traffic and all of that, and they don't really want that. This is also the reason why, so there's a question in the homework about this, why Google, Yahoo, and Bing might necessarily recommend different pages. Because they're using different algorithms to try to determine which page is most relevant to your search term, even if you put the same term into the different search engines. Okay? A lot of times there's a lot of similarity between what they return, but the actual ordering might be a little bit different. And one of the things you'll find is that the different search engines start to emphasize different types of sites. But I'll let you see that in your homework, and maybe we'll talk about that a little bit more on Monday if you've got questions. And so what we want to do is, at least in some way, is try to think about how can we actually try to go about determining relevance. Okay? Do you have any ideas? What might a search engine do when it's trying to determine how relevant this page is? What are things it might look at? Okay, so we can compare the frequency of the search term. So if we're searching for cat videos, if we have a web page that just repeats the words cat videos, cat videos, cat videos, cat videos, cat videos, cat videos 100,000 times, that's a really relevant page, right? Maybe. Yep. So maybe we're going to look at the date it was published. So we're going to give a little bit more relevance to things that are more recently published. You would have thought? Oh, same one. Okay. Yeah, another idea? Okay, so the popularity of the page. How might we look at the popularity of the page? How would you actually necessarily quantify that? Okay, so how many times the page was clicked on? That's a good idea. That's a little bit hard to implement in practice because that's not something that's innate to HTML or to any of the web languages. So I think Google would love to use that information. That's a little bit harder to get at, but we're going to try to approximate that in some way. Okay, other ideas on what might we want to look at when we're determining how should we determine relevance? Other ideas you think we might want to examine? The title of the page. Okay, does our search term appear in the title of the page? So again, maybe we title our web page cat videos, cat videos, cat videos, cat videos. Okay? So these are all great ideas. I think we've actually hit most of these. So frequency that the search term appears in the text, or possibly the metadata. So there's all this metadata associated with the web page. Most of the time it's to help your browser understand how to display the web page, but you can actually put information in it as well. It won't actually get displayed in your browser, but it still gets transmitted to your computer. We'll talk about that more in about 2 weeks when we get to the internet. But that's there, and Google can certainly search that. We said presence of the search term in the title or maybe section headings. And we've sort of mentioned maybe relations between various web pages. So we're going to try to get at sort of popularity through that way. And what usually are these relations between web pages that we might want to look at? What's a standard relationship between web pages that connects two pages to each other? Okay, so one is citing the other. We can certainly do that, and like Wikipedia will have that. You go to the bottom, and it usually says here are more references. But then buried in that reference, there's a what? There's a hyperlink. It actually links to that web page. And so that hyperlink is something that gets put into the HTML files that Google can then search through, and that's something it can easily pick out and flag and sort of process. Are what pages does this one particular page link to? Okay? So maybe we can use that information. If we have a whole bunch of web pages and we're sort of monitoring what does every one of them link to, maybe we can try to, in some way, approximate popularity in some sense to see what's going on. Why are some of these strategies not optimal? These are all really good ideas, but why do we not necessarily want to bank on one versus another? Right. Right, so exactly as we said, we could have this page that just recycles the words cat videos, cat videos, cat videos, cat videos for 100 gigabytes, and that's all it does. It would probably get flagged really high on that first criterion because that's all the page contains, 100 gigabytes of the words cat videos, cat videos. But when we come down and actually look at that as humans, if Google were to recommend that page, are we going to go back to Google the next time we have to do a search? No, because does it actually tell us anything or provide any videos whatsoever? No, it would turn out to be sort of a stupid page, okay? And so the reason why some of these strategies may not be optimal is they're easy to cheat, okay? There's a huge amount of money. If you're going to develop, if you have a company and you're going to start developing a website, or you're going to develop websites because you're hired by a company, whatever the case may be, getting traffic to your website is a huge game, okay? And so you can try to register with Google, with Yahoo, there are a bunch of different places online to say, I want to advertise my company. Okay, and part of this does, so this is why Google has sort of, there's those recommended pages at the top where they'll mark it, here's an ad. Someone's paid them a little bit of money. Now the Google search engine still works, so if you're searching for, I don't know, cat videos, it's not going to want to show you dogs. It's going to try to show you something related to those keywords. So it's either going to try to sell you a Netflix streaming service, or here's a cat adoption center. Okay, because that might be relevant to the individual words, cat videos. But it's going to give you some ad. And so if you can try to cheat to raise your score in Google, number one, maybe you come up more frequently in the ad circulation, but then if you can increase your score and increase that relevance, you're going to come up closer to the top in the actual Google search. Because how many people go to page 3 when they do a Google search? Does anybody really ever go to page 3? No. So if your website and your company is always appearing on page 3, how much traffic are you actually getting? Very little. And so this is another reason why in a lot of cases how Google, Yahoo, and Bing determine the relevance is also proprietary. Number one, they don't want you scooping them and trying to make your own search engine. Number two, they don't want companies being able to completely game or cheat the system. Okay? And so they're constantly making updates to these algorithms, trying to weight different things, look at new things as they come up with different ways to quantify certain relationships, to then influence their algorithms and keep people from being able to game the system. Okay? So, what is ultimately used in a lot of cases, or at least certainly by Google, is some variation of what's called the PageRank algorithm. And so this was developed in the 1990s by Sergey Brin and Larry Page. There's a picture of them not from the 1990s down on the bottom. And just as sort of a note, it's sort of interesting that Larry Page would develop, this big algorithm for how to do searches and ranking web pages, because PageRank is not called that because it ranks pages. It's PageRank because it's a ranking algorithm developed by Page. Okay, so it sort of works out as a pun in this way, but that's what it was actually named for. And anyway, so once they developed this in the mid-90s, Page and Brin later went on to found Google And I think most all of us today know what Google is and what Google does. If not, you should Google what Google is. Okay? So the point is there's a lot of money in this. So the big idea here is for PageRank is it's not necessarily on its own trying to determine relevance. Certainly when we're looking at the relevance of a page, we want to make sure that our search term appears in some way, shape, or form in that page. You know, if we're searching for cat videos, we want to find something that actually has a video of a cat or the text cat videos or something like that. That's certainly one part of relevance, but another part of relevance is exactly what was mentioned, sort of popularity, or what usually I regard as sort of authority. Do we regard this website as being particularly authoritative? Is this something other people found useful, whether they were looking for cat videos or anything else? Okay? And so the idea behind PageRank is we're trying to quantify this idea of authority. Okay? The way it works is suppose that you're an erratic web surfer, so we've got our little cartoon web surfer here on the bottom. And you're going to start at some page. I don't know, you start at Wikipedia, you start at CNN, doesn't matter. Pick some web page. And you're just going to start randomly clicking links. So whatever web page you're on, you're going to say, well, here are the 45 hyperlinks on this web page. I'm going to randomly click one of them, click. And you're going to go to that page. Okay? Every time you visit a page, you're going to tally and say, oh, I just visited this page. Then I clicked. And now I'm on a new page. Well, I visited that page. And then in this algorithm, you're then going to go and look at all of the hyperlinks on the second page, and you're going to randomly pick one of them. You're going to click it, go to a new page, tally. And the idea of trying to get at popularity or authority is which web pages do you visit the most? If a page is very authoritative, if it's very useful, do you think a lot of people will link to it, or is no one going to link to it? How about those two things correlate? If no one's linking to it, is it really maybe that authoritative of a web page? No. So again, if we had our web page that was just 100 gigabytes of the words cat and video followed one by another, is anyone ever going to link to that when they say, oh, here's a great site for cat videos? No. They're going to completely ignore it. Okay? And so in this sense, would that be a very authoritative page? No, it wouldn't. It's going to score real high on the frequency of the search term, but it's going to get a terrible authority score. And so this is what the PageRank algorithm is trying to do, is to see how do we try to estimate this authority, engage, is this website or this web page something good or is it something meaningless? And so then what Google or Yahoo or Bing is going to do is try to do an all of the above approach, where now maybe we go back to these couple criteria we had, and say, well, our frequency score, this page was like a 99.9% hit. This was a great web page from the search term, but it had a really terrible authority score. And so we're going to sort of weight those two together when we're actually determining relevance. Likewise, could we have a really high authority page that is completely irrelevant to our search term? Sure. We don't really want that to be relevant either when it's returning the things. So we're going to start to balance all of these things out. Okay? And that, again, what is that right balance? I have no idea. If you want to know, go get a job at Google, sign the non-disclosure agreement, and then don't come and tell me. Okay? So, basically to summarize what we just said then, pages that are linked by lots of pages will be just visited more often. As we're sort of going around and randomly clicking, if your page has more links going to it, you're going to get to that page more frequently. And so maybe these pages are more informative. That's why people are linking to them. And in some sense, we can try to infer something about authoritativity. And then, of course, pages that are sparsely linked to are not going to be visited that often by an erratic surfer. And so we're going to make the conclusion that these pages probably aren't really that important, or they're not really that authoritative. And that's the whole premise behind the PageRank algorithm. So for an analogy, can think about sort of trying to do some crowdsourcing here to see what's going on. So certainly, we're going to start with a graph. Notice, do we have a directed or undirected graph down here? It's directed. In this case, is it cyclic or acyclic? It's cyclic. Okay. Is it weighted or unweighted? It's unweighted. Okay. So what we're going to do is forget the web for a moment. We'll come back to that momentarily. But sort of ask a question. You and 4 friends are setting up pairwise study sessions for an upcoming exam. It's not impractical, I don't think. Okay, so you compare your schedules and you know your 4 friends and who's sort of good and who's sort of not. And you sort of rank your preferences on who you want to study with, who's available to study at good times, and say, well, I only have time to study with one person, so here's the person I would prefer to study with. Versus someone else might say, well, I have time to study with 3 people, and these are the 3 of the 4 I would prefer to study with. And so what we've done in the graph is sort of ranked your preferences. Who would you prefer to study with? So this arrow, or this edge, linking from you to 1 says you would prefer to study with person 1. Okay? Or maybe you would prefer to study with person 4, but 2 and 3 are not your preference. Those really aren't your best friends. Those are friends of like 1 and 4 who happen to be your friends, and you don't really like them, and person 2 doesn't shower all that often. And so just, it's not, let's do something else. And so everyone sort of comes up with this. And so, you know, from this information, can you start to guess who the most authoritative person is in your study group? If you only have one person to study with, who do you think that person you would want that person to be? Does anybody want to take a guess from looking at this graph what you think that might be? Yep.
I would take a guess and say maybe 2.
Okay, maybe it's person 2 because you notice there's a lot of traffic going on around person 2's vertex. Person 2 actually preferred 3 people. Person 1, you, and person 3. 2 people preferred person 2. Again, persons 1 and 3. You didn't. Love is not reciprocal in this case. Okay? But, okay, so it could be person 2. And so another way of sort of phrasing this question is, maybe instead of saying who's the most authoritative in the study group, what we're maybe asking is who's the most popular study partner, which you might sort of infer as asking the question, what? If you're the most popular study partner, what's probably also going to be true? Well, you might have the most arrows pointing to you, but think about it sort of in the more general context. If we're just forming study groups, if you're a really popular, everyone wants to be your study partner, what's probably true? You're probably the smartest. Okay. Again, that's a subjective measure. Okay, we're going to ignore IQ for the moment, because that's not always exactly what we want to get at, but that's sort of the presumption. So maybe what this is really asking is of this group of study partners, you and your 4 friends, who's the smartest? At least with regard to the material on this one particular exam. I don't know. So think of this as sort of a motivating example, and we can actually use the PageRank algorithm. We haven't completely gone into it yet, but sort of this is as a motivation. What are other types of things we could solve with it that might make it a little bit more concrete and a little bit more tangible? Okay? We'll come back at the end and answer this question. Okay, but this sort of gets us thinking. Any questions on this before we proceed? We'll get to the answer. Hold your horses. It's not person 2. Okay, so what we're going to do now is think about constructing a very, very simple internet. And when I say simple internet, we're now going to have 4 web pages. Okay, really big one, I know. And we're going to label those web pages just A, B, C, and D. I don't know, maybe A is Wikipedia, B is CNN, D is stonybrook.edu, and C, I don't know, pick something else. We've got 4 web. It's YouTube, good. We've got 4 web pages. And we can look at the different hyperlinks that these web pages have. So what we now have, again, we have our directed graph. Happens to be cyclic in this case. And is it weighted or unweighted? Still unweighted. Okay. What each of these edges is showing is, in this case, so web page A has a hyperlink that will take us to web page B. In this particular case, web page B also has a link that will return us to web page A, but B also has hyperlinks that will take us to page C and down to page D. Okay? So the way we're going to do PageRank now is we're going to put our surfer initially on some web page. Let's assume for the example we'll work today, we're going to put our surfer originally on web page A. And what we're going to do, rather than just counting the number of times the surfer goes to a web page, we could do that, but we can get a little bit more information if we're just a little bit more clever in how we do this, is just try to ask ourselves, what's the probability at some point that our surfer is on a particular web page? Okay, so at the very beginning, if we say we put our surfer on page A, well, then we know the probability that our surfer is on page A has to be 100%. We knew at the beginning that's where he was, or she was. So we have a 1, and then likewise, there's a 0% probability that they're on B, C, or D. Okay? So that's our starting point. What we now do then is we'll go through all 4 of the pages and say, well, there's this surfer that has this 100% probability that it's on page A right now. What happens to that probability if we equally distribute it amongst all of the outgoing links? Okay? So we can start and go through all 4 of the pages. Well, page A has 100% probability, as it turns out. How many outgoing links are there from page A? There's just 1. So what happens to that 100% probability at this step? Well, how many different ways are there for the surfer to go? How many paths can he possibly take? There's just 1. Everything that's on A has to go over to B. Okay? Now, in principle, we should do the same thing and say, well, there's 0% probability on B. How many outgoing links are there from page B? There are 3. We can go back to page A, we can come down to page C, or we can go down to page D. And so we would want to take that 0% probability and distribute it over those 3 links. Now, in this case, 0 divided by 3 is still 0, so we don't really have to do anything. Likewise for page C, how many outgoing links do we have? We have 2. And so what happens to that 0% probability that's on page C? Well, it gets evenly distributed between pages A and between page D. And then likewise, we'll do the same thing for page D. So what we find after going through all of this, well, again, right now, because we know our surfer was on page A, we only have to consider that one. But what happens to that 100% probability when we do sort of the one iteration here? It's going to go to page B. Okay? So after doing one step of PageRank, we see that everything had to get transferred to B. And notice now, there's a 100% chance that the surfer is on page B after we took that one step, because it's the only place he or she could go from page A. You're not allowed to stay on the same page. You have to click. Unless, of course, your website links to itself, but please don't do that. That's a really nasty way to game this algorithm, FYI. Okay? So now what we're going to do is, again, the idea of the server is we're going to keep clicking links and keep clicking links and keep clicking links and see what happens after we've clicked lots and lots and lots and lots and lots of times. Okay? So now what happens? Well, we're going to do the same thing. We're going to go over all of our different pages and take whatever probability is on page A and distribute it over all of the outgoing links from page A. And we're going to take the probability on page B and distribute it amongst all of the outgoing links for page B. And the probability on C and distribute it over all the outgoing links from page C, likewise for page D. So what happens to the 0% of probability that's on page A? Well, how many different links does it have to possibly go to? It's just the one, but it's 0% probability. This is a stupid question. Let's move on and do something more interesting. Okay? So we come to page B. And there's 100% probability that our surfer was on page B. How many different places can the surfer now go on his or her next click? There's 3. The surfer could go, as it turns out, back to page A, could come down and left over to page C, or it could go down to page D. So what happens to these probabilities? How much probability gets transferred to each of those pages? We send a third of it to all 3 of them. So we might say, well, there's a third that comes over here. There's nothing remaining at B. A third comes here, and a third comes here. Okay? Does anything happen when we look at what's going out from pages C or D? No, because there was no probability that we were on page C or D. Okay? So we don't really have to consider them. But after this round, sure enough, okay, so I put decimals here instead of fractions, but you now notice after we've done now these 2 steps of PageRank, we now have, there's basically a 1/3 probability that our surfer is now either on page A, C, or D. We've now started to see it sort of disperse through our very simple internet. Okay? So now, again, in the idea that we want to keep clicking links, we're going to keep doing this over and over and over again. So now what happens? Well, we started with, we've got this 1/3 probability on page A. What happens to that 1/3 probability? Which web pages does it get distributed between? Well, how many outgoing links does page A have? It just has the 1. So all of that 1/3 of probability has to go to page B. Okay, so we can put that down here, and we'll add that up. Okay, there's 0% probability that we're on page B, so do we have to do anything right now? Nope, move on. We've got a 1/3 probability that we're on page C. How many outgoing links does page C have? 2. So what do we do to that 1/3 probability? We split it in half, and we send half of it to page A, and the other half to page D. Well, what's 1/2 of 1/3? 1/6. So we'll put 1/6 down here on A, and we'll put 1/6 down here on D. And then lastly, we have to consider this 1/3 of probability on page D. How many different links can that probability go to? It only can go one way, and it has to go to page B. So we put another 1/3 down here. When we add all of those up, we'll get, for our next step, that there's 1/6 probability that we're on page A. So 2/3 probability we're on B, 0% chance we're on C, and 1/6 that we're on D. Okay? So let's verify that we did this correct. I'll clean up the screen a little bit here. And sure enough, 0.17 is at least to 2 digits, that's 1/6. 0.67 to 2 digits is 2/3. And so this is exactly what's going on. And so what we could do now is we could keep going and keep going. We could keep iterating this process over and over and over again, because we want lots and lots and lots and lots and lots and lots of clicks. This sounds really tedious, right? Okay. So on the next one, we would take that 1/6 of probability on A, we would send it over to B. The 2/3 probability on B would get distributed 3 ways. So now you have, what would it be? 2/9 probability going to A, to C, and to D. Nothing happens at C. And that 1/6 probability in D goes back to B. Okay, so this starts to get a little bit funky, all right? And so actually we can go through and do that if we were to look. So what do we have? The 1/6 here. We could put a 1/6 on B from A, so we're done with that. This was 2/3, which divided by 3 gives us 2/9. So we can send 2/9 over here, 2/9 down to C, and 2/9 down to D, following all of those outgoing links from B. Nothing happens on C. And the 1/6 from D has to come back up to B. Well, and 1/6 plus 1/6 is just 1/3. And if we represent that in ninths just for comparison, we get 3/9. And again, when we add all of those probabilities up between the 4 web pages, what do we end up getting? What's 2/9 plus 3/9 plus 2/9 plus 2/9? Just 1. Should this always be 1 when we add them up? Yeah, because there was 100% probability in the beginning, and it's just sort of, we're just moving it around. So think of this as sort of a big game of whack-a-mole, where you see, here's the mole, you whack it, and sort of move it over another place, and it just sort of gets distributed around. Okay, we can do this. And sure enough, we'll compare here for a moment. And 0.22 is 2/9 to 2 digits, 0.33. And so that's exactly what ends up happening. Okay, I think at this point we stop going through this step by step. Well, so we can do one more. It shows a round 6 here where we do the same thing again. So take that, what was it, the 2/9 on A, move it over to B. The 3/9 on B, divide it 3 ways, so send 1/9 to A, C, and D. Split the 2/9 in C into half, so to send 1/9 to A and D. And then take that 2/9 that was on D, send it back up to B. You can get round 6 where we start to get probabilities like this. Now, what we can do if we don't want to have to keep going step by step by step by step, the math of where this came from is a little bit more than I want to go into here, but I want to show you it can be done. We could actually look and take like the limit as we take a very large number of steps. What happens to the probability? And it will converge in this way to a certain set of probabilities. And what we find is if we were to go an infinite number of steps and just sort of keep clicking and moving this probability around this graph, what we're going to see is we ultimately get about a 0.21% chance, or a 21% chance, that our surfer is on page A, 43% chance it's on B, 14% chance on C, and that same 21% chance it's on D. So of these web pages, that if we've let this go for a really long time, which of these pages do you think would be considered the most authoritative? It's going to be B, because we notice as our web surfer is going around this internet, that ends up being where the surfer spends most of the time. Okay, it's not even half of the time, and certainly if we had an internet with 1 billion pages, is the surfer ever going to spend like even 10% of his or her time on any one page? Not even close. All we have to do, though, is look at the relative numbers to see which page is the most likely, even though it may not be likely as one alternative at all. But then that's going to help us to do authority. And so we could rank this now to say, well, B is our most authoritative page. A and D, as it turns out, are equally in second place for being authoritative. And C, as it turns out, is our least authoritative page in this graph. Okay? Does that sort of make sense on how this works?
So basically you want to have like hyperlinks that link out to pages that link back to you, aren't you?
Well, so ideally what you want are pages that link to you. Because the more pages that link to you, the easier it is for the surfer to sort of get to you. But then what you want on top of that is someone who's authoritative to link to you. Because if they're authoritative, then they have a lot of probability. That's how we get it authoritative, which means every time you go, they're transferring to you. What you'd like is for them to uniquely point to you, so that every moment of that authority score they get just gets sent in your direction. And of course, the nice thing about this is this really is sort of crowdsourcing. Do you have any control? If you're a website publisher, do you have any control over what pages link to you? Or even more specific, of any authoritative web pages that link to you? Suppose we're going to concede that CNN is an authoritative source. Do you have any ability to route CNN to your website? No. So is this somewhat of an easy system to game? No, you need someone at CNN to actually recognize, oh, you've got a good website that has some interesting information. Let's link to it. And then PageRank will pick up on it, and suddenly you're going to start to see your authority go up because someone who the algorithm already recognizes authoritative has said, you've got some interesting stuff to discuss. Okay? And so in this way, we really are sort of crowdsourcing what's going on, but in a way trying to keep, well, everyone's treated equally and treated fairly, and we try to prevent people from gaming, but then by looking at the different behaviors and the different actions that people take, we can try to estimate this idea of popularity or sort of authority when it comes to search engines. Other questions on how this algorithm actually works? So I know there's definitely a homework problem that's going to have you sort of look at this a little bit.
When you were going through it, how can you like cut the 1/3 and 1/6? How can you cut them in half?
You just divide it by 2. Oh, why? You look at the number of outgoing links. So suppose, we wanted to take this, I'm guessing that's 1/9 probability on C. We notice that C has 2 outgoing links. So we send 1/9 divided by 2 up to A, and 1/9 divided by 2 over to D. So because we're just going to take whatever probability you have and just equally split it amongst all links, because we're just going to randomly pick one of those links to go. And so then likewise here, I think B, in this case, that's a 4/9, would be the actual fraction. Again, noticing that B has 3 outgoing links, we would divide that 4/9 into 3 parts and send one of those parts back to A, one of them down to C, and one of them down to D.
Everyone we were doing, we just pick a random one.
Well, so if you wanted to think about the surfer's actually now just a discrete thing floating around, then you would just pick a random one and just move the surfer. By sort of going to the probability, we can sort of see what's going on in all times with just a little bit more work, and this will converge a lot faster. I don't want to necessarily get into that, per se. But does that make sense? Yep. Other questions? Okay. Then let's discuss this a little bit more. Clear the slide off here. Okay. So what we finally get, that final set of probabilities, that sort of round infinity score that I gave, these are the page ranks. And as we've already said, sort of the higher the score that we get there, that higher that probability, the more authoritative we would regard that website. Okay, because that says people are linking to it, but more importantly, authoritative people are linking to it. Okay? And so as we've already sort of said, what probably happens is that search engines are going to use some hybrid of this, where they're going to weight this authority score also with some sort of text processing to see, did your search term appear in that particular website? Weight those two together, and possibly also date accessed or date modified, things like that, to do it. But what PageRank essentially adds is this idea of credibility or authority. I just want to note, what we discussed here is not entirely the pure PageRank algorithm. There are some pathological cases we'll discuss here in a moment that what we discuss can get fooled by. And so there are a few simple workarounds that we could add in to get around them. I didn't want to necessarily go into that in full detail, though. If you're curious, there's a link here for a lot more information on PageRank itself, at least the algorithm that was published 20 years ago that sort of deals with some of these more complicated cases as well. But this is the general gist of what's going on. Okay? So, stepping back and sort of going through the main theme of this course now, what are some of the math concepts that we want behind PageRank? Okay, so clearly there's algorithms, because PageRank is an algorithm. Okay, but there are a couple others that we can now throw in. So one of the things that we should see, would you expect that final set of probabilities? So we go to round infinity. Well, in that particular example, we started our surfer at website A. Should that final set of probabilities depend on whether we start our surfer at web page A, web page B, C, D, or some combination of them? Should it matter? No, because it's this idea of authoritativity is a property of the internet, not necessarily a property of of the surfer and the path that he takes or she takes. Okay, and so the math idea that this is getting at is that of convergence, which is to say, if we're going to converge, it can't depend sort of where we started. Okay, and so as we take more and more steps and go through this, do we converge to that final set of probabilities? And the answer is this algorithm does. It's proven, that's well beyond the scope of what we're going to do, that this PageRank algorithm will converge. So no matter where we start our surfer, we will eventually, that round infinity in essence, will get the same numbers every time. Okay? Basically, I said we're not going to really talk about how we got those final numbers. I'll just put a little note here. We need some linear algebra tools. If you know the term eigenvalues, maybe you've taken a linear algebra course like AMS 210, the eigenvalues of a matrix are very important, what lead to these. If you don't know what eigenvalues means, we're not going to spend any time on it. Don't worry about it. Okay? But what they can also tell us is more to say that there are tools that exist that can help us with this, is try to predict how many rounds will it take until we're really close to being converged. Okay? So we saw in this last example, when we looked here, are those round 6 probabilities all that far off from the round infinity ones? No, we've seen that within about 6 rounds, we've actually got a pretty good approximation. We can actually quantify that and predict that to say that, well, we know within 6 rounds, we would be pretty good. Okay, maybe you could design another internet. Certainly, if there were thousands or millions or billions of pages, it's probably going to take a lot more than 6 rounds. It might take 1 million rounds or 2 million. I don't know how many. But the idea is we can use some math tools and we can try to predict what is that rate of convergence. How quickly from where we start will we get to something that starts to closely approximate what we're actually after? And that might be important from this algorithm analysis perspective. When Google's trying to figure out the relevance, it has to know how long do we let the simulation go before we eventually just cut it off and say now we can actually try to associate relevances and authoritativity with a particular web page. Okay? And so the last thing that's sort of a neat math concept to come in here is that final set of probabilities will end up being called stationary points or fixed points of the algorithm. And here's what that means. So suppose we started our surfer with this set of probabilities, where there's a 3 in 14 chance that the surfer was on page A, likewise on page D, 3 out of 7 on B, and 1 out of 7 on C. If this is a fixed point, okay, so think about that word fixed or stationary. If we apply the PageRank algorithm to this set of probabilities, what do you think will happen? If this is truly that round infinity, that converged result that gives us the relevance or the authoritativity of that page, what's going to happen if we run another round of PageRank on this distribution? It should stay the same. That's exactly right. It's a fixed point. It is fixed by that algorithm, which means whatever we put in is going to be exactly what we get out. Okay? And so we can verify that. Actually, so let's remember these numbers let's take a moment and transfer them back up here. So we had, what was it? It was 3/14 here. It was another 3/14 here. What did we have? 3/7 on B and 1/7 on C? I think that's what we had. Sure. Okay. So if we were to do the round of PageRank now, what we would have to do is say, well, we have this 3/14 on page A. Well, that has to go over to page B, because that's the only outgoing link, again, from A to B, and we can move that over. Okay. So for our 3/7 on B, how many different places can we send that 3/7 to? We can send it to A, B, and D, or sorry, A, C, and D. And what's 1/3 of 3/7? 1/7. So we can put, there's 1/7 over here, 1/7 over here, 1/7 over here. Okay, so we're done with that one, we're done with that one. What happens to that 1/7 from C? How many different places can we send it? 2. It has to go to either A or D. And so we divide that 1/7 in half, which gives us 1/14. And we put one of those 1/14 on A, one of those 1/14 on D. That clears that one up. And then what happens to that 3/14 probability from D? It all has to go back up to B because there's only that one outgoing link. So we put another 3/14 here. And when we add up, what's 1/7 plus 1/14? It's 3/14. And so we recover that probability. What's 3/14 plus 3/14? It's 3/7. What's 1/7? 1/7. Okay. And we've already seen 1/7 plus 1/14 is again 3/14. And so this is the idea of a fixed point. So this is a surefire way to determine, do we have a fixed point? Have we reached that final set of relevances or of authoritativity scores? By just sort of looking in, let's plug in whatever those scores we think they are, put it through the PageRank, and if we get the same set out that we put in, that's the fixed point, there's our final answer. Okay? And it turns out, when we're looking at different algorithms or different functions in mathematics, these fixed points can actually have quite a bit of utility in a lot of cases. And certainly here, when doing this PageRank algorithm, it's really important. Okay? Any questions on that? Real quick? Okay, then let me clear off the page. And just FYI, for the homework number 5, this is the slide with this big example that the problem is referencing. Okay? So we come down, and so we can see that that was our fixed point. We can verify that. Okay, so I mentioned before that we weren't quite using the true PageRank algorithm. We were using sort of a simplified version. The true one tries to get rid of some pathological cases. And so I've plotted 2 of these pathological websites up here. Take a look at these graphs for how these different hyperlinks work, and can you see the problem with the left one? Why might PageRank not be a great algorithm, or why might it have issues on that left web with those 4 pages? What's the problem? Right, so if you go to C, notice there's no way to get out of C. WebPage C doesn't link to anyone else. So eventually, what's going to happen to all of that probability as we keep clicking and clicking and clicking and clicking and clicking? It's all going to end up at page C, which is to say C is 100% authoritative and A, B, and D are meaningless. Is that necessarily right? No. Okay, so if we really want to think about this, because now is this potentially something that could happen in the real web? Could you get some jerk who wants to game PageRank and just makes a web page, somehow fools CNN and all of these authoritative places to link to it, and doesn't actually link to anyone else? Could that conceivably happen? Yes. Congratulations, you just broke Google. Okay, you won't actually, because they've come up with ways to fix this. And likewise, so if we look now at the internet on the right, again with our same 4 web pages, A, B, C, and D, but now pages in different order, or with different link patterns, what's now the problem? Right, so regardless of where you start, you're going to end up down here in this loop in C and D, because you notice we can loop between A and B, but once we come down to C and D, there's never a way to get back up to A and B. Okay, and so in this case, if we were to let this PageRank go on and on and on and on and on, what do you think that final set of probabilities would look like? It's going to be 50-50 between C and D. Okay, and again, so that says C and D are equally authoritative, And again, A and B are completely irrelevant. Is that necessarily true? No, it isn't. So what are different ways that you think you might be able to modify our algorithm to look at this, or to try to deal with these cases? There's no unique answer to this question. But how might you modify what we were looking at to try to prevent some of these issues from happening if someone actually gave you an internet that looked something like that? What would you do? Any thoughts? Okay, so one possible solution that has been employed in certain ways is to say, well, let's ignore then that infinitely converged, that fixed point solution, and why don't we suppose that we'll just start our web surfer at one of the 4 pages randomly, and we'll let, okay, this is a small internet, so we'll keep the numbers small. We'll let that surfer click around, let's say 50 times, and look at the distribution that we get at the end. Is 50 going to be a big enough number that, like on the left case, where everything has now gone to C by 50 iterations, or everything is down at C and D on the right by 50 iterations? Probably, you're going to get a lot on C, and you're going to get a lot on C and D, but you're probably still going to have a few things up in A, B, or A, B, and D. Okay? It may not be much. So maybe we even want to prune it back and go to 25. Okay? But we can sort of just cut off our algorithm and just stop iterating at some point. And maybe what we'll do is then we'll run a couple simulations where one time we start our surfer on A and see where he or she ends up after 25 iterations. Then we'll start the surfer at B and see where it ends up after 25 iterations, and start to compare those different things together to try to get out of this trap where everything just gets sucked down into one spot versus another. That's something that might be done. And in fact, I believe in the full page rank, at least the one that's published, that's one of the tricks that's used, is we never actually let it go necessarily to the infinity because we would get caught into some of these traps. Versus if we restart it periodically, we can keep our server from getting just trapped down in one of those regions. Okay? Does that make sense? Okay, so we'll come back to our study group problem. So now we have, okay, here's our graph again. So we've got you're in the center. We've got our friends 1, 2, 3, and 4. And so how might we try to go now figuring out who's the most popular study partner, or in the less crass version, who's the smartest of your group of friends? How could we go trying to answer that? What do you think we might try? Yep. Well, so it might be who has the most arrows pointing towards them. That could be. But what we're trying to get is maybe instead, who's the most authoritative? And so we can try to do this whole PageRank idea to see, well, if we just said, here's something that we're going to do, let's sort of go around and see who ends up being the most authoritative. Because you could think, maybe, you've got the most arrows pointing to you. I think that's actually true in this case. You've got 3 out of 4 possible. Maybe it's just because your schedule's really open. Does that necessarily mean you were the most authoritative amongst your group of friends? Not necessarily. Okay? Certainly, looking at the number of arrows and the number of links is a good place to start, and it's a good estimator in a lot of cases, but it's not necessarily going to be exactly the same thing. Okay? So instead, maybe what we want to do is run our PageRank algorithm on this. Okay? So we could start now a friend surfer at some random person. So I don't know, pick you or one of your friends, and start to go through this process and say, well, now we're going to say there's, I don't know, let's say 100% probability that our friend surfer is on you. That sounds dirty. What happens? So how many different places can this friend surfer go to on the next step? Well, how many of your friends are you willing to work with? Or are you able to form a study group with? Oh, there were 2. We could go up and work with friend 1, or come over and work with friend 4. So that probability is going to get split in half and sent to 1 and 4. On the next round, we would consider, well, what happens to the probability that was up here on friend 1? So we had a half. It can come back to us, or it could also go down to friend 2. So we get now a quarter. Friend 2 has a quarter. And what about the 1/2 probability that's over on friend 4? It has to come back to us. That's the only outgoing link. And so we add that 1/2 back in, which gives us a 3/4. And we can continue doing this on and on and on and on and on. I don't think we need to go through this in full detail. Okay? But after we would go through, so I crunched the numbers, and what we would find out is you can use that page rank to examine the fixed point. And so what we end up finding, again, so think about going all the way out to that infinity point, okay, after we've taken an infinite number of steps here. And we can see that sort of your page rank score for you is 0.372. So a little over 37% of the time, that little friend surfer is going to be on you. About 23% of the time on friend 1, 14 on friend 2, a little under 5% of the time on friend 3, and about 21% of the time on friend 4. So in this sense, who do you think would be the smartest person in your study group? Of course it's you. Okay? Who would be the next smartest person? Friend 1. Who's the dullard? Friend 3. Okay. There's a reason we didn't put names on these people. We'll just call them friends 1, 2, 3, and 4. Okay? But we can use this idea to try to get this authoritativity by looking at relationships between all of these things and bring a lot of those tools from graphs and from algorithms together to try to understand these relationships. Does anybody have any questions on this, on anything we've discussed in the search engines unit, the PageRank examples here today, or anything else moving forward? This is a great time. So this is the end of our search engines unit. Yep.
Like on the homework, when we do like problems like this, like how do we know like which one to choose as we go along? It's like, you know, like if it splits to 2 different ones or 3 different ones, how do we know which one to go from after?
Okay, so the idea is that every time we're at every iteration, so the question was how do we sort of know where to move the probabilities to and which ones to choose? So the starting point I will give you. I'll tell you initially, you know, at the initial step, put the surfer here. Okay, I think I said in the homework it's put it at B, but check the homework. We end up using the same web. We end up using the same one. Where we started on A in class, I think I have you in the homework started. It's either B or C, I don't remember which one. So you would initially start, again, so with the round 1, which is given, we know that the probability is at that point. What we're going to do at any step is then go through all 4 of these web pages and say, well, for page A, how many outgoing links does page A have? Just has the 1. Well, in that case, we have to divide our probability into 1 and ship all of it over to that page that it's linking to. Likewise, for page B, we notice there are 3 outgoing links. So we would take whatever probability is on page B. Right now it's 0, but it could be something bigger at some later point in time. Take that, divide it into the 3 ways. And we're just going to divide it evenly and move it to move that 1/3 of that probability to all of those 3 pages. Likewise, in C, how many outgoing links are there? 2, so we would take whatever probability is in C and divide it by 2 and move it to those pages. And then you sort of sum up what happens after we've divided it all up to then figure out what's the new probability for A, what's the new probability for B, for C, for D. That's the end of the round. Do it again. I think I asked you to go through 3 rounds of this. But again, check the homework assignment for the exact wording. Okay? Other questions? Yes? Yes? So do videos count? Absolutely, because all we're doing is looking for the URLs. So it's completely conceivable, depending on what your search rate was, that YouTube might actually have a couple hits. So for the solutions that will get posted on Monday, since this was a topic that none of you could use for your term paper because I wouldn't allow it, I chose Global Positioning System for mine for when writing up the solutions. And Amazon came up a couple times, which is not necessarily an informative web page per se. It's commercial. But it did come up, and so I just put the URL in there. Yep. So again, just copy the URL. Yeah. Don't get bogged down on what the actual content of the page is. We're just now looking to compare URLs. I'm trying to see, in some sense, do the different search engines give you sort of a similar set of web pages? Do they give you different sets of web pages? A lot of times you'll see there's some subtle differences in how they order them. I'd be willing to guess that for probably all but 3 of you, Wikipedia will be in the top 3 of all 3 search engines. Because whatever term you're going to put in is going to have a Wikipedia page. Is Wikipedia, despite the fact that it's not guaranteed to be authoritative, does it tend to be pretty authoritative? Yes, and it ranks highly in a lot of these things. Okay? And so that's the goal of number 3, is to sort of compare what are they doing and do you see different things when using different search engines. Okay? Other questions before we move on? Okay. Then I think we've got about 15 minutes left. We're going to go ahead and just ever so briefly start our next unit, which is our last unit, believe it or not. And shift gears and talk about Google Maps. Okay, so we're not going to start here today, but someone asked a while ago if we would see the bridges of Königsberg in the puzzle. I said, wait for it. There it is. But we'll come back to that next week. Okay, so this unit, everything's sort of labeled Google Maps, but we really are going to cover 2 different technologies in this unit. We're going to have both Google Maps and the Internet. And so maybe the question that I'll pose at the very beginning, what's the common theme? Why do we relate Google Maps and the Internet, and do we put them in the same unit? What do you think might be the common thread? Yeah.
Google Maps, you have a lot of different locations, and you want to get in between locations.
Yep.
And for the internet, like you're on Wikipedia, and you want to get to like StonyBrook.org, so you
Yep.
gotta go in between like sites.
Okay, so very close. So the answer, the proposed answer here was, in Google Maps, there's a lot of locations, and what Google Maps is trying to do is to get you from one to the other, sort of like route finding. And on the internet, you've got a lot of links, and so maybe you're starting at Wikipedia, and you want to get to, I don't know, StonyBrook.edu, and you want to see how do you get from one to the other. This is very close. But yes, the common thread, as it turns out, is going to be pathfinding. How do we get from some point A to some point B? Okay? What exactly is point A and point B? We'll talk about this. It's going to be a little bit different between Google Maps and the Internet. And there are some things where, even though that's the common thread and that's the common theme, there are some different considerations between Google Maps and the Internet where how we actually go about trying to solve that problem will be a little bit different. But that's sort of the umbrella that's going to link all this together. So maybe for the second question, why did I save this unit for the end of the semester? Any ideas why?
Well, we have more information about how Google Maps works with the satellites, and more information about how the internet works with like search engines.
Right, so we're going to see a lot of the units come back in some way, shape, or form. So you all probably, you know this already because you've used it. Does Google Maps make use of GPS? Yeah. So is that going to help us understand Google Maps a little better since we've already done GPS? Does the internet have to, store and transmit and securely transmit information? Yep. So we're going to see all of those units come back. Does the internet need kidneys? No, but it turns out graphs are going to be really important. And at the end of the day, Google Maps and the internet, they're running algorithms. Certainly the search engines operate on the internet. And so are we going to see a lot of that algorithmic analysis and this idea of looking at algorithms and what are the different steps and procedures? Are we going to see that come back? Yeah. So we're going to see in some way, shape, or form something from every one of the previous units come back, which makes this sort of a great unit to end the semester with because we're going to get to sort of take a swan song over everything we've seen so far this semester. And just as the final note, I'm pretty much going to eliminate the trademark symbol on Google Maps from this point on. Just pretend it's there. Okay, so sort of start with our normal way. We have Google Maps. What do you use Google Maps for? Okay, so directions. How do I get from point A to point B? That's what a lot of Google Maps is used for, but is that the only use for it? What are other things? Yep. Just see where something is. So yeah, we're looking for food. Restaurants near Stony Brook, New York. And of course, it tells you there are some great restaurants in Chicago, which is not useful, but that's because you were just zoomed out too far. You can see reviews. So it links in, and it'll try to go either you can leave reviews through Google, or a lot of times it'll show you sort of a Yelp ranking or something like that. But you can start to get a lot of information. Yep. Okay, so for when doing route finding, not only how do you get from point A to point B, but how long does Google Maps anticipate it will take you to get from route A to route B? Because that's sometimes an important consideration. Uh-oh, there's a quiz in the 8:30 a.m. class. I better make sure I'm there by 8:20 just in case there's extra traffic. What time should I leave? Well, how long is it going to take you to get there? Okay, that can be useful. Other things you use Google Maps for? Yeah. Okay, train schedules. So Google Maps works with a lot of the different municipal and, governments and agencies to try to include train schedules or subway schedules. Amtrak schedules are usually on there. In a lot of cases, certain airlines will be on there showing you, you can get a flight from Islip to Baltimore. One probably leaves in about an hour and a half. Okay? And it'll show you here's the route, here's the airline information if you wanted to see that as well. So it actually brings in more than just roads. In particular, if you're also down like in the city or something, it also can give you walking directions, biking directions, and so it knows more than just sort of the roads, but it takes into account a whole bunch of different venues for transportation to try to provide you information as well. Yes, I mean there's a lot of information buried here in Google Maps. Okay, so I think we've covered a lot of it. So certainly finding places, getting directions. We didn't actually mention this one. You can use Google Maps to locate traffic jams. Has anybody done that before to say, again, sort of what's the anticipated time? Uh-oh, there's an accident on the LIE. I better allow more time or take Sunrise or Northern State or whatever you want to do. Okay. I don't know if anyone's big into exercising. Has anybody ever used Google Maps to either plan a hike or a run or a bike ride or something like that? I've done that several times. So that's one possible use. Sometimes there's just exploring the world. How many of you have used Street View before? Everybody know what Street View is? So we can come over to Google Maps, and let's do the Bean, Chicago, Illinois. And you can come down, and if you've never clicked it, there's this little guy or little person button down here. You can come to Street View, and there's different, a couple things. Okay, turn on. Yes, thank you. Go show the image. And so you can start to see, in some sense, it'll try to take you in, and okay, well, there's two people that just happened to be there when Google was passing by. And a surprisingly sunny day in Chicago when they were taking these pictures. But sure enough, there's the Bean, and here are people that stand there like statues through all time, which is to say, at some point, Google will go and update this photo database, and you'll suddenly get a new group of people going through. But we can sort of move, and you can use your arrow keyboards and try to see, or arrow keys, sort of see what's going on. Notice the people have all changed now. We can move maybe in a different direction slightly, trying to see where's one we can go. Anyway, but you can go and you can start to explore the world and actually see what it might look like from a person's perspective. If you were to sort of walk around or bike or be on a bus, riding through some city or through some geography, okay? And that's pretty cool. If you've never played with that, seriously, over the weekend, have some fun. There's some neat stuff in there. Okay. All right. So basically, what it ends up amounting to, when all is said and done, is when you sort of put all of that together, Google Maps is basically a search engine for geographical information. Because you're going to go search Google Maps. Where is this city? Where is this restaurant? What shopping centers are by me? What museums are by me? How do I get from here to there? These are all sort of questions that you might ask a search engine that all involve geography in some way, shape, or form. And so if you regard Google Maps in that way, we can start to bring all of our tools from search engines over and then start to just narrow that consideration to say, well, what is it about geography that we might have to approach a little bit differently? And so for some of the other things, some old screenshots, I took these from Google Play a little while ago. You can start to see, driving directions. You can see traffic jams here in the Bay Area where, in red that says, uh-oh, a lot of traffic. And it might actually even just tell you, oh, there's a slowdown on I-880. I don't know, I've not spent a lot of time in the Bay Area. But you can do that. Another interesting thing about Google Maps, again, when you're looking for just where are cities, is it can do overlays. And so if you were curious about municipal boundaries, for instance, so what actually is the city of Stony Brook, New York? And you can go and type that in, and it will outline out for you in this red region, well, there's the municipal definition of Stony Brook, New York. Notice there's this big chunk missing here, sort of in that center-eastern corridor. What is that big chunk? It's exactly where we are. The university is, I guess, not, at least not as far as Google Maps is concerned, is not officially part of Stony Brook, New York. I'm guessing they probably went by zip codes, and the university has its own zip code, which just got sort of sorted out.
I think we have like 790, but like there's straight up like zip code for something like 794.
So I think 794 is the university and 790 is the city, or it's one of those ways. Anyway, yeah, there's I don't know how they actually get this overlay. Someone was really bored one day and started putting in a bunch of municipal boundaries. Beyond that, so remember we had our election day yesterday. Maybe you wanted to know what political district you were in, or how close are you to the boundary to see how badly are you gerrymandered. Okay, and so you can go, and this is the New York's first congressional district for the U.S. House. And again, Stony Brook is sort of the little blue line there. So clearly we are most certainly here in New York's first congressional district. If you were curious, you can go to house.gov and it'll show you any of these. If you want to look up any particular congressional district, it'll show you the area that it encompasses. The areas don't necessarily have to be nice. New York 1 actually has a pretty relatively straightforward boundary. It's a little bit jagged here on that western end, but it's not too bad. We could get things that are a lot more complicated for the overlays. Anybody want to take a guess what part of the United States this is discussing? It's North Carolina. You can see sort of buried underneath all of that mess of lines. There's Raleigh, there's Wake Forest a little bit north of it. So these were actually, they no longer are in use, but these were two congressional districts that North Carolina had up until about 2 years ago, when the court said, no, those are really bad districts, you should redraw them. Okay, but so the idea is that Google Maps, regardless of what you're trying to do, can make overlays as simple or as complicated as you want, but to describe these different regions and sort of visually display the information around them. Another thing that's neat is Google Maps has terrain and satellite imagery available. So we've said Google Maps relies on GPS in certain cases. Part of that is for doing images. So again, I took an image here, and I apologize, the resolution is a little bit low on this big projector. Where do you think this satellite view is from? It's Manhattan. And how do we know that? Well, you see there's Grand Central down here, the Chrysler Building right there. You see here Lexington and 41st, 42nd, 43rd, and so on and so forth. But we can actually start to see what does it look like from down or from up above. What's also kind of neat, anybody ever play SimCity? Any one of the variants? Okay, there's a couple hands that go up. You can actually try to do a 3D satellite view, where Google Maps will try to then go and use different combinations and different camera perspectives to reconstruct what the different buildings look like. And so suddenly downtown Manhattan starts to look, or rather this is about Midtown Manhattan, starts to look much more like Midtown when you actually see here are the skyscrapers and their different heights and different shapes. And you can actually see now this is much more identifiable as the Chrysler Building than it was just sort of looking at it top down. You know, you sort of look for that spire and that Art Deco top that you just don't really see when you're looking at it directly from above. But so there's a lot of neat things buried in here. And so one of the issues that you might want to be worried about then, if there's all of this satellite information, all of this geographical information, are there privacy issues that come into this? Or security issues that come into this? Absolutely. And so for one instance, okay, so now where are we? We're in DC, okay, it's the White House. And so we've got our top-down satellite view here. What do you think happens to the White House if you go for the 3D satellite view? It looks exactly the same as the top-down satellite view. It won't actually show you the 3D. The government has petitioned Google, and Google granted it that this is a restricted zone, and it won't give you that information. That way you can, so in principle, with that, you could try to figure out what are the dimensions of the White House. I mean, this is all stuff that's publicly available if you dig around, but they're just, from the security reason, they're not going to show it to you. Okay. There are other areas also. I believe the Pentagon has a similar lockout, various federal agencies, certainly in this country and in others, that are locked out where Google restricts that information because they're either security or privacy concerns. Okay? And so you can go and see that. And so I think this is probably the place to end for today. I'm not going to post these like 4 slides we've done. We'll just put these as part of Monday's notes. But so work on your homework this weekend, revise your term paper, play around with Google Maps. Let me know if you find anything fun. Otherwise, have a delightful weekend. Thank you for your attention, and I will see you Monday morning.